So our next speaker is Stefano Schiavon. Stefano is going to be talking about healthy buildings, thermal comfort monitoring. And let me tell you a little bit about Stefano. Stefano Schiavon is a professor of architecture and civil and environmental engineering and associate director of the Center for Environmental Design Research at the University of California, Berkeley. Stefano's research is focused on finding ways to reduce energy consumption in buildings while improving occupant health, well-being, and productivity. Dr. Schiavon has researched sustainable architecture, air conditioning, and occupant satisfaction as well. Stefano is also involved in the Center for the Built Environment and Sinverbest project. Stefano, it's a pleasure seeing you again. Really looking forward to your talk, and so the floor is yours.
Thank you very much. So we spend most of our life inside buildings. More than 90% of our life is within a building environment, and that building environment affect our health, affect our well-being, affect our ability to get our job done, affect our ability to learn and to enjoy life. And when we think about how to organize and assess this indoor environment, there are many dimensions and today we hear some of them, from ergonomics to air quality, from acoustics to lighting. Today, I'm going to focus specifically on one, the thermal environment. And I will not focus on extreme thermal environment that could create heat stress, even if I have a couple of slides at the end in case someone has some question about it. I will focus more on moderate condition, the one that the large majority of the population is exposed to. And I will try to make 2 points. The first is that there is a high level of dissatisfaction with this dimension. And the second, if you're measuring just air temperature and relative humidity to assess thermal environment, you're not capturing probably some of the other important variable and what is the ground truth, what people think about that space. A couple of disclosure before I start my presentation. This work has been supported by the Singaporean government through their National Research Foundation. And also I received funding from the Center of the Building Environment here at UC Berkeley. It is a consortium of 50 industry related to manufacturers, building owner, company that design, construct, and maintain buildings. So there are many ways to assess the indoor environment. We can perform measurement, and sometimes these are very important, like when we measure air quality and its different characteristics, for example, particle CO2 or VOC. But also another way to assess building is to ask people what they think about the space that they occupy. And the Center for the Building Environment for more than 20 years went around buildings in the United States, but not only. We cover also some other part of North America and several parts of Europe and Asia. And we ask people what they think about their space, what they think about the lighting, the acoustics, the thermal comfort, the air quality, the furnishing, the arts on the wall, how clean is the space, and so on. And by looking at the data, we found that overall, roughly 2/3 of the occupants are satisfied with their space. And here the results are mainly about office environment, but we also have data for other type of environment, like for example, schools or residential buildings. And when we look at the things that are not going well, we notice that there is high level of dissatisfaction with acoustics, in particular acoustical privacy, the ability of other people to hear what you are saying or you being bothered by what other people are saying, and thermal environment. And if I go a little bit more on detail here in this slide, you see the satisfaction level. And these are data from roughly 900 buildings, almost 900,000 answers. This is by far the largest database available in the world about this topic. Usually the other database have subset of, let's say, 50, maybe up to 100 buildings. We collect this data set in more than 20 years of research. And so we can see that overall, people are quite satisfied with the ability that they have to interact in building. And they also quite satisfied with the amount of light. But even in this category, that are the highest rating, we still see only a satisfaction level, something around 70 to 80%. We are not able to achieve higher level of dissatisfaction. And then results are more or less the same for other components of the indoor environment, like, for example, satisfaction with the furnishing, satisfaction with the visual comfort, satisfaction with the cleaning of the space. But then if we go to the lower 5 parts, then we see dissatisfaction levels that are much higher. For example, in the case of air quality, only 55% of the people are satisfied and 25% of the people are dissatisfied with the exposure that they have with the perceived air quality. And when we go to temperature, we roughly have 45%, 43% that are satisfied and 39% that are dissatisfied, even lower quality related to acoustics. So when we look at this number, we need to start to think, what do we compare this number to? If, for example, we look at the standards, the building codes that are the regulation that we should try to meet, the aim there is to try to achieve at least an 80% satisfaction level for thermal comfort. And so we can see here that we are very far from it. We are roughly half of that target. Another way will be to compare with other industry, the satisfaction level that people may have with, for example, products. And if we look at that, successful company has satisfaction rate that are in the range of 90 to 95%. And unsuccessful company, usually they end up around 80%. And so we can see here that we have a lot of room for improvement. Another way to look at this is to look at certification program. So in buildings, you can get certification for how sustainable they are or how much they promote well-being. One of these certification programs is the WELL certification in the United States. It's a performance-based system for measuring, certifying, and monitoring features of the building environment and how they impact health and well-being. And they look at aspects like air quality, water, food, lighting, if they promote or not physical activity, thermal comfort, and if they promote or not mental health. And so here is an example of a sub-point related to the thermal environment. In this type of certification, the more points you get, the better it is. And what we see over here is that you get 2 points if you get at least 80% of the people satisfied, and you get 3 points if you get at least 90% of satisfaction. And you can see here that based on the data that I showed earlier, we are very far from achieving this goal. Typically, we found that it's only maybe few percentage, maybe 5% of buildings are able to achieve at least an 80% satisfaction rate. When we look at why we're achieving such a low satisfaction rate, we notice an interesting trend. And here are the results for any type of building, but here I'm focusing only on the temperature. And the reason why we see such a high level of dissatisfaction is that people do not have enough control over their environment. Another interesting point that we notice when we look at the data is that people tend to be happier when they are close to a window, in particular if that windows can be open or not, therefore they have control over that windows. Moreover, they tend to be happier in private office, probably because they can adapt their environment to their specific needs. Another interesting result is when we compare satisfaction levels for male versus female. And we've done this analysis in two ways. One, we look at tweets that people are doing related to their built environment. And what you see here, the result from our own survey. What we notice is that we find a higher level of dissatisfaction among female. And in a very bothering way, we found that the problem is the strongest in the summer for people that are feeling too cold. And in a building, we would like to see that if someone is uncomfortable, for example, in winter, they're uncomfortable because it's too cold, not because it's too hot. Why we would like to see that? Because that would mean that we are using the energy in a clever way. We are not wasting energy to make people uncomfortable. Similarly, in summer, we would like to see a situation where people feel too warm or too hot if we have some uncomfortableness, but we would not like to see, like we see in this case here, that 20% of the occupants are unhappy in summer because it's too cold inside the office. And when we look at who is feeling too cold, 76% are female, meaning that at the same time, we are wasting energy, we are making people uncomfortable, and that is disproportionately affecting women. I will not go into the detail why this is happening, but in case people have questions later on, there are some ideas of why that could happen. We care about energy and people's satisfaction at the same time because buildings have a large impact on the built environment, on the planet. They are responsible for something around 30% to 40% of the total greenhouse gas emission. And when we look at how electricity is used in the United States, 75% of that electricity is going into building, and most of it is for heating, cooling, ventilating, and providing lighting to people. So what I covered until now, I touched that there is a high level of dissatisfaction in building, particularly related to thermal comfort, and there is an energy waste connected to that. So what can we do? People may say we want to rely on standards or building codes, but unfortunately, that are kind of the base. You do not achieve a high level of satisfaction by just trying to comply with codes. Here's a picture of an office that I assessed many years ago that comply with all the requirements of temperature, lighting, ventilation, and noise. Maybe this is minimizing some extreme health risk, but is unable to provide a joyful and satisfying environment. When we look at high quality design, when the budget is not a constraint, when the design team is among the best available, still in those situations, we found situation of unhappiness. For example, here is a study that we did at the Kresge Foundation in the United States after that they renovated their headquarters. And what we found here is an example of a typical workspace with the need of a desk fan for keep people comfortable in summer, a heater under the desk to keep them comfortable in winter, earphone to protect from the noise around. So another potential solution is green certification, like the one that I mentioned before, the WELL or the LEED certification. But when we look at differences in satisfaction in LEED certified building versus non-LEED certified buildings, here we compare results from something around 10,000 people in one group and 10,000 people in the other group. Overall, we found little to no differences in satisfaction level. So we have a problem here. We have a high level of dissatisfaction. Buildings use a lot of energy that have an economical impact for the owner, but also an environmental impact for the planet. And the typical tools that we are using, like building codes or certification program, are not working too much. So what can we do? Probably the most important step forward is to recognize that the existing paradigm used to create comfort in building is not working. Right now, we think that there is one temperature or a set of temperature and relative humidity that can satisfy everybody. And that's the way that we provide this service to people. We think that there is a specific temperature that can make everyone happy. And if we make a parallelism to other fields, it would be like to say that there is one chair size that can fit everybody, or that you may find a specific size of shirt or shoes that is okay for everybody. And the objective is to try to find the shoe size that satisfies the highest majority of people. And that's how we now provide comfort into buildings, the same temperature for everybody. But it's obvious that we have different needs and we have different expectations. And therefore, we need to move towards a future where people are able to customize their thermal environment. How? One example is work that we have done here at the Center for the Built Environment to develop chairs that can heat and cool people. We found that these ones are both effective from a thermal comfort point of view and also from an energy point of view. Unfortunately, these products are not yet available in the market. We have other solutions where, for example, the HVAC system try to provide something similar to what's happening in airplane, a situation where people can control the temperature and the airspeed close to the area where they are. Or there are more affordable solutions, like, for example, the use of fan to keep people warm in summer. And I will come back to this solution later on, because fans are a very effective way at the same time to provide comfort, but also to save energy during the cooling season. One big advantage of fans is also that they are affordable for a larger part of the population compared to air conditioning. In heating, we have other solution that has been proven effective. Here we have two examples. One is a foot warmer, and the other one is a radiant panel. As you can notice, I didn't use the typical personal comfort system that people use, that is a radiator located under the desk. Those type of radiators that use 1000 watts have the problem that they are very energy intensive. And they are something around 10 times or 5 times more energy intensive than the solution that I show over here. Usually, solutions that are contact-based in heating tend to be more energy efficient and more comfortable than solutions that rely on warming up the air through convection or radiating people with heat. And this type of personal control solution now are becoming accepted also through certification program. Here's an example from the WELL certification that now allows the use of personal comfort system as a better solution compared to only a general control of the space. So I showed that there is a high level of discomfort in building, that typical solutions do not work, and personal control can be a potential solution. Now I will spend a few slides to give a hint of why measuring only temperature and relative humidity may not be sufficient to characterize the complexity of the thermal environment. So people tend to produce heat constantly inside their body, and then they need to release that heat to the environment. And they release heat through convection, through radiation, plus through the type of work that they are doing. And when activity is high, also evaporation through sweating or breathing play an important role. Here, the most important point is that in typical condition, when people are not at high physical activity, when they are, for example, working at a desk, the radiant environment is as important as the convective environment. And so if you're measuring only air temperature, you're only capturing half of the problem. Because the radiant environment, that is the heat exchange between your body and the surfaces around you, play an equal important part. And our body tends to be happy when the amount of heat that is generated inside your body is more or less the same as the amount of heat that is released. And if you produce more than what you release, for example, that could be when you are doing physical activity or when you are in a very hot environment, your body will start to sweat first, vasodilate, and try to counteract that inability to release heat. On the opposite, if you're in a situation when you release more heat than what you produce, for example, in a cold environment, then your body will go in hypothermia. And for example, it will vasoconstrict, and therefore your hand and your feet will get very quickly cold. So when we look at the thermal environment, we need to look both at personal factor, like for example, how much heat you are producing, that's named metabolic activity, and how much clothing you have, basically the level of insulation between yourself and the environment. And then we need to look at environmental parameters, things that we can measure. And among them, the most measured one is air temperature. And sometimes air temperature and relative humidity. Relative humidity is not very important in typical condition indoor, but it becomes important when the temperature is high and the mechanism of sweating and evaporation become the main mechanism for releasing heat. The other two parameters that are rarely measured are mean radiant temperature, that is basically somehow related to the average temperature of the surfaces around you, and the airspeed. And I will spend the next couple of slides to give some example of mean radiant temperature and why air velocity is important. So here is an example of a person close to a windows. If you are in winter and you have a weak windows, for example, a single pane windows, you will have the experience that the closer you get to that windows, the more cool you will feel, or the more cold you will feel. That is because your body releases heat through radiation to that windows. Something similar may happen if you're in front of a fireplace. Even if you're not exposed to the warm air generated by that fire, you still get some warming effect due to that radiation effect between the flame and the body. And sometimes this is negative, like for example, here, if you're close to a windows in winter, or sometimes we use actually this solution to create a more comfortable solution. This is this example of a radiant system when you have pipes embedded in concrete or in ceilings, when you have warm water or cold water to condition the space. The other example, the other dimension is airspeed, the use of air movement to provide cooling. We think at the Center for the Built Environment that the air movement is an underappreciated technology, and we are pushing very hard to have a bigger presence in the built environment. Why? For a couple of reasons. First, air conditioning a space is very expensive. It's expensive, the equipment that you need to buy, and is extremely expensive to operate. Moreover, the environmental impact of air conditioning is large, both through the energy that they are using, but also because they use refrigerant that when they are leaked out to the environment, they have a large impact on greenhouse gas emission. On the opposite, fans are cheaper, and they could become much cheaper in the future because fundamentally the technology is way simpler than an air conditioner. An air conditioner needs a compressor, needs to have 2 heat exchanger or 2 coils, it needs to have a fan, and it needs to have a connection between the inside of the building and the outside of the building. On the opposite, a fan is basically an electric motor with some plastic blades, and therefore fundamentally it's a much cheaper. Moreover, a fan can operate with a small fraction of the energy used by an air conditioner. And we have done a lot of research to prove all of these points. For example, that among the most cost-effective solution that you have to reduce energy consumption in building is to increase the temperature set point in summer and decrease them in winter, and provide personal comfort solution to keep people equally comfortable in those situations. An example in the study that we have done in a high-end office environment in Singapore, we started with the typical condition of 23 or 73 degrees Fahrenheit without a fan, and we measured that only 58% of the people were finding the space acceptable from a thermal point of view. But when we increase the temperature point to save energy, and we provide people with fans, in this case, this one were ceiling fans, we notice at the same time an increase in satisfaction up to 91% and a substantial reduction in energy consumption. And we started to see the presence of fan being more common now in building. Here's an example from the Commonwealth Club in San Francisco. Usually, when we advocate for wider range of temperature, we often are confronted with the equation that you see over here. This equation was built several years ago from colleagues at LBNL, at Lawrence Berkeley National Lab, and colleagues from Finland, that show that in order to have people be high performance, the temperature should be kept constant at 72 degrees Fahrenheit. And if you deviate from this optimal temperature, there will be a reduction in performance. We reanalyze this equation. We try to recollect all the data that they have used to develop that equation, and we expanded also that model by adding more recent studies. Both with the original data and with the expanded data, we found that that equation is not reliable. We can basically fit any model with equal level of performance with the existing data. And so overall, we found that there is not an optimal temperature that can increase performance. And here, keep in mind, we are focusing on typical condition found in building. We are not referring to farmer workers or construction worker outdoor. We are looking at temperature that range between 20 and 30 degrees C. And so overall, for typical condition in buildings, we didn't notice an effect of the thermal environment on performance. And we think that people can be comfortable at many temperatures. What is important is providing them with the ability to control their environment. And so the main standard that is used to assess and design for thermal comfort is provided by the American Society of Heating, Refrigeration, and Air Conditioning Engineers, and is named ASHRAE Standard 55. These standards take into account all the parameters that I described before, like physical activity, clothing, temperature of the surfaces, air velocity, and relative humidity. And it's mainly using a model that is named PMV, the predicting mean vote, and it's trying to predict how many people will be dissatisfied in that environment. We assessed the performance of that model, and we found that is able to get the right answer only one time out of 3. In case you want to see how this model works, we offer a tool for free. It's available online at the link described over there, where you can input the different variables that I mentioned earlier and see if a specific space comply or not with that standards. We also have there other tools related to other thermal comfort standards or other type of heat stress conditions. In case you need to manage a lot of data points, not only few, we also develop a Python, open source Python library where you can input a continuous stream of data and calculate different type of thermal comfort indexes. But coming back to the accuracy of that model, I mentioned earlier that when we assess this model against more than 55,000 data points, we found that it gets the result correctly only 1 time out of 3. So 2/3 of the time, the model is not able to predict what people will feel. And when we tried to assess if the model was able or not to predict the percentage of dissatisfied people, we found that basically the model was never able to control the environment. If you look for solution of creating comfortable environment, out there you will find several situations where people will claim that a uniform environment is more comfortable. From a scientific point of view, we do not find this result. The problem is not that the environment needs to be uniform. The problem is that you need to tailor your space to the specific needs. So let me conclude with the 2 takeaway messages. The first one is that if you measure air temperature and relative humidity as the only way to assess the environment, you are missing other important variables. And I recognize that measuring those other important variables is difficult, in particular in the case of air movement. And so asking people what they think about their space, it's a reliable and effective way to assess the thermal environment. Here we show an example of a tool that we developed that can be embedded in the Apple Watch, and where people can give feedback about, if they feel that it's hot or cold in the space, or if just feel that it's fine. So ask people first, measure later. Another important point is that not only what you monitor matter, but also the granularity of control that you provide is important. And if your system can only control air temperature and provide the same type condition for all your workers, then you do not have the ability to tailor the specific needs of the people. People have different expectations, they have different physiology, and therefore you need to provide a personalized thermal environment. Thank you very much.
Thank you so much, Stefano. What can I say? This completely revolutionizes the way I think about the office environment that actually I'm in right now, which has no airflow whatsoever and no individual control. I'm in a box that has no windows. I have a small pane window embedded in a door that I shut so that I reduce the acoustic noise. My satisfaction level is not high. So this is so important to talk about this particular aspect, and I'm sure it's a topic that isn't top of mind for many of the people in our audience today, and that's one reason why I really wanted you to participate in our conference today. So what you're pointing out and is most aligned with the talk that Dr. Mosier started with is you've got to put the person back into the equation in determining what temperature to set and how to measure properly what is the satisfaction level with the thermal comfort, and not go on technology alone, because it just gives you a number. It doesn't tell you what is really being felt. So with that, I would like to ask you some questions. That I have one question from the audience. So this question is, what are your recommendations on how to effectively manage cold stress in a control room where temperatures are generally set to keep machines cool, but not very comfortable for control room operators? Any thoughts on that?
So usually this one we are sometimes already outside the range of thermal comfort, and we start to go into the range of heat stress. And in that case, in the case of cold heat stress, there is quite a lot of experience. For example, in the case of people that work in a refrigerated house for processing food like meat or vegetables. And usually PPE is the first step of defense, like increasing the level of insulation. The problem of all of these solutions is that they tend to reduce the comfortableness of people of using them. They may reduce the ability to move and manipulate things. And therefore, there's been some exploration on some type of active heating clothing where you have a battery and that one provides some local heating. Overall, there is not much advancement or yet not enough solution out there. There are not widely available and affordable products that can, for example, systematically keep your hand warm in those situations. And coming back to the comment that you did, today I made an example for thermal comfort, but similarly for other dimensions of the built environment, the ergonomics, the lighting, the acoustics, and to a certain degree, the air quality, bringing people at the center is important. And the other important aspect is that when we solve the more extreme situation that create, for example, a high noise environment that create a damage in the long term, we need to start to think also of less extreme stimuli that in the long term create tiredness, fatigue, inability to concentrate, and then can cause problem later on.
Yeah, very important. Okay, there's a piggyback question from the same questioner. What are your recommendations with working in dry rooms? Dry rooms are oftentimes found in battery research facilities with low humidity. Do you know anything about dry rooms?
No, I'm not an expert in that type of situation, but thermal comfort is not substantially affected by relative humidity if you are in a typical indoor condition. And that can be noticed in the presentation. If you look at the comfort tool, basically you are allowed to stay between 0 and 100% of relative humidity if you are at the typical, let's say, 70 to 75 degree Fahrenheit condition. But then there are other reasons why humidity become a problem. From, for example, the dryness of your mucus, like mouth, nose, and eye, to other issues, like, for example, related to electrostatic condition. There's been also some research related to the risk of indoor transmission of disease, COVID, influenza, and some preliminary work, maybe not yet ready to be implemented in practice, that look at the relationship between temperature and humidity and the risk of transmission of disease.
Okay, and let me kind of expand the reach of your talk to smart buildings. So these, if you can define a smart building and how effective you think these smart buildings are, which are intended to optimize the energy usage and comfort level using algorithms. So can you comment on whether there's hope for implementing the science that you have created in those kinds of environments?
Buildings are getting smarter, and we have seen a positive revolution both in the amount and quality of the sensor available and the ability to process those data. So that has been done. I think there has been progress and has been overall positive. Something that we didn't do enough progress is not on the sensing and analysis, but on the actuation side. So I learned that there is a problem. I recognize that that is a problem. I want to do an intervention, but my machine, my building is unable to provide a type of granularity. And that's why in my presentation, I pushed so much on the fact that we need that level of personalization and control.
Yeah, that's Yeah, go ahead, please.
And the other issue is that often this smartness is related to issue of energy and security. And unfortunately, they try to optimize for these two parameters, and they use people as a kind of, and comfort as a constraint, meaning that, oh, you should not allow, for example, the temperature to go above and below a certain point, or you should not reduce the amount of outside air below a minimum level. And this is a typical issue on when you frame an optimization process. What are you trying to improve, and which are the limits of how you try to use your system? And I'm challenging my own community to say, we should try to maximize the experience of people while trying to not use too much energy, too much money, or violating other constraints, for example, connected to security.
You have offered so many options to air conditioning and heating during your talk. And so I'm wondering what you think might be the headwinds or resistance that facilities managers, corporate real estate operations people might have to doing this coworker control aspect that you're talking about. Have you encountered that, and have you been able to overcome that in any way?
Overall, there is nowadays a much larger awareness of the problem compared to 10 or 20 years ago. So people are more aware and they are more willing to adapt. And particularly after COVID, there's been a strong realization of the role of, for example, the amount of air that you bring in, the level of filtration. So I think that the amount of barriers has been reduced. One barrier related to thermal comfort is just the availability of product out there. I show you a couple of examples that work decently well and they are relatively affordable, like that floor mat that keep your feet warm. But I think that there could be a lot of new product coming out that could make the process even simpler. For example, we know that when heating is in contact with the person, it works better. That's why, for example, we enjoy so much an electric blanket or a heated seat in the car. But having the same solution in an office environment is more challenging because we need to recharge that chair, or that chair needs to be connected to power. Thinking about solution that will be wirelessly charging that system or provide better battery, that would allow, for example, for more option. Another barrier connected, for example, to air movement is that many people do not like to see something spinning in the environment, ceiling fan or a desk fan. And you see over here in this last slide, the Dyson one, that you don't see the blade spinning, but then you have other problems related to cost, related to noise, and related to the amount of energy. Because when you need to basically pressurize a plenum, like in the case of the Dyson, it's just harder from a physical point of view. And so again, thinking about product that could provide the benefit of one solution without the negative of cost or more noise, it will be what is missing.
Yeah, and is the autonomous control of heating and cooling also possible if temperature changes during the day?
It's possible, and for example, a smart car already do it now. If you are in a high-end car nowadays, they try to learn what you like and in time provide what you want. I don't think that this is transferable easy to building. Buildings are not like cars or like airplane that are mass manufactured, and therefore they tend to be weaker, less reliable. And so we may not need some kind of smartness. It's not so hard for a person to change the temperature of a fan or the speed of a fan or change the temperature of a mat under your desk. Maybe just having a sensor that turn it on and off when people are leaving will give you both control and avoiding waste of energy. And so I doubt that we will see what is already possible and common in some type of product ended up in buildings. Even smart thermostats are mainly used to turn things on and off when you're not at home, or preheat the house before you go back. But their ability to adapt to your need is somehow limited.
Again, back to human-centered technology. Thank you so much. It's a pleasure seeing you and having incredible information at our hands. And now we can be even more hopeful that in the future we'll be able to be warm when we want to be and cool when we don't. And yes, when we want it. Okay.
Christina, thank you very much.
All right. Take care. And now we will break for our lunch.